So today I'm going to talk about surface code and um, primarily about the logical qubits in the surface code. And so again, error correction, quantum error correcting code is not about correcting the code, but also we need to make a logical code that operates as a qubit. So we're not using physical qubit, we combine physical qubit to make a logical qubit. So therefore we need a logical gate. So we're going to see how the logical qubit is working in the surface code and how the logical gate is working. But in fact, these are not two different things. So you cannot make a logical qubit without logical gate. So you cannot talk about logical gate without talking about logical qubit. So I'm just listing all the items as a concept, but in real, this thing going all together in the surface code. So about the logical code, a logical gate, we're going to talk about X gate and Z gate and C not gate today. And I think that's going to be more than enough for understand today's material. All right, so the material that I'm going to use today is this one, the paper in 2012 surface code written by Flower et al. And this is, so far I found it the best paper to understand the surface code. And I hope you can take a look at this paper and read it. And it's not an easy paper, but I think I haven't found better paper than this. So I'm not saying it's not well written. It's very well written. It's hard only because the surface code itself it's kind of not familiar to us yet. So I'm gonna open this up and just use this as my main material. All right, so I'm gonna skip the first part here. Basically, I'm gonna put up the pictures. The reason I'm using this paper is there has a nice picture here, and I don't want to just copy the picture. Instead, I'm just use this picture to explain everything. So here you can see the surface code is in this configuration. So you can see the black dot and the white dot. Black dot is a stabilizer, white dot is a data qubit. They are configured in a lattice configuration. And in the figure below, there is a figure B and C, and there is A, B, C, D in the data qubit here, A, B, C, D, A, B, C, D. So every time you run a surface code, there is, in this case, 8 timing, so it's 8 steps. So this one cycle, 8 step is one cycle. So let's look at this one first. So in the X stabilizer, you go for ABCD sequence. So first of all, X stabilizer take a projection measurement or projection operator on the data qubit on north. So A, and then B, west, and then C to the east, and D to the south. So you can see that there are ABCD register, and then the X operator or C0 operator, which is a projection operator, which measures the eigenstate of X operator on each data qubit, is written here. And every time you begin the cycle, you kind of you want to initialize your stabilizer, but not data qubit. You don't want to do anything on the data qubit except for this projection measurement. You must initialize your stabilizer to the ground state. So in this paper, they uses G and E for ground state and excited state. Ground state means 0, excited state means 1. So here, GE, you can just replace G for 0 and E for 1. So here again, so every time you begin, before you take any projection measurement, you want to initialize your state measurement qubit as a ground state, 0 state. And then it ends with the measurement here. So here, this is a typical projection operator sequence. So that's because we have an X stabilizer. And now if you look at this one, it doesn't look like the similar. Well, what we have to do is we need to take the Hadamard on in the beginning and the end, just before taking a measurement. And then we want to take a CZ gate instead of this one. Well, look at this one. It's kind of weird. There's no Hadamard, and this control and target is kind of switched up, right? So instead of having a control on the stabilizer qubit, it has a control on the data qubit. Everything else is similar, but still there's something more going on. There is I. What is I? So if I begin with one by one, so here we're supposed to use the projection Z measurement to be something like this. But in fact, you can replace this by the opposite direction, because in fact, what we have here is Hadamard. So because Hadamard is, sorry, not Z here, it's X, is X. Okay? So using this identity, you can just replace this into the flipped CX gate, C0 gate, and that's what is going on here. So instead of having the same sequence, it makes the sequence only using the C0 gate. And the reason being is, usually we don't implement CZ gate. In the real quantum computer, there is no CZ gate, because CZ gate in this case also it can be replaced by C0 gate with the help of a Hadamard gate. So it tries to give you the realistic version of the surface code really implemented in the surface code in the quantum computer. So we have only the C0 gate. And because we flipped around the CZ gate with the C0 gate with upside down, we don't need a Hadamard, so there's no Hadamard. But when you do the sequence, you want to make the timing right? You don't want to get it, some stabilizer going in a third stage and some stabilizer going in a fourth stage. So we want to get the timing synchronized. So you want to get the third, fourth, fifth, and sixth to be the measurement qubit or C0 controlled qubit. And then when you do that, there are two steps missing on the Z stabilizer, which has the H Hadamard gate on the X stabilizer. So you want to throw in some identity gate here so that get the timing as 8-step right. Okay? And then everything else is same, so you get the ground state initialization and the measurement. So you can see that basically what happens is in each cycle you get the 4 measurements going on for each stabilizer, each black dot. So at the first measurement, the black dot is acting on the data qubit on the right. So you can always pair the black dot with the white dot to the right. And if there's none, so for example, if in this case, on the boundary on the right, there's no data qubit on the right. So in this case, this data qubit is resting at that time. So on the right, let's say it's the qubit C. So it's fifth step. So this data qubit is not doing anything on the fifth stage. So it can be, so if you're looking at this data qubit and you want to implement the sequence as a quantum circuit, then you want to throw identity gate on the fifth stage here. And similar for upper and left and bottom part. So there are two types of stabilizer, in fact. So one is, so in this case, there are only two. One is the stabilizer that has all 4 data qubit, and stabilizer that has only 3 data qubit attached to it. So this is the full stack, and this is the third, I mean, it's kind of semi-stack here. Is it clear, the picture? It makes sense? All right, so let's look at more picture here. So here again, It's also a nice picture, so I want to introduce it before we move on to this real business. So here, it's kind of visualization of what is going on when we move on time. So here, the vertical line is time. This is not real configuration. It's just imaginary timeline here. And there is a configuration on the bottom. And let's say this is our beginning of time. And we took the measurement of the stabilizer, and plus means 0, minus means 1. So which means that the eigenstate of the data qubit on this time at this stabilizer is plus 1 eigenstate, which means that we measured 0 when you look at the measurement qubit here, and so on. And then this is one cycle. This is after finishing one cycle. And then we took another cycle, and then we took the measurement, and we got here. So here's a time kind of a period that takes time to finish one cycle. And after one cycle, you have these qubit right here, and this red bar. Whenever we have a red line, there is a stabilizer attached to it. There is a change on that stabilizer. So you can see that this one changed to plus, from plus to minus, minus to plus, minus to plus, plus to minus, and then minus to plus. So you can get the error correction going on here, but as I said, you're not correcting error right away. You just detect the error. Okay, so when you do that, I mean, you don't even do that when you do the surface code, but you kind of assume that since we have a change in these two stabilizers, you kind of guess that there must be a Z error going on in the data qubit and X error going on in between these two data qubits, and so on, right? And how about here? So I had something detected here, okay? And then I can't see anything possible to have this error, right? So the only way we can have an error from minus to plus here on X stabilizer is there is a Z error nearby. But if there is a Z error nearby, then this data stabilizer has also been detected. The Z error has to be detected by this data stabilizer. But there's nothing here, right? I mean, it's just one thing. So in this case, we kind of think that this is the measurement error. So it's M means measurement. So the error not occurred only because, but error is not occurred at the changes only because there has been an error when we measure the data stabilizer qubit, and so on. But again, when we actually implement the surface code, we just take the measurement and record it to the classical computer or another device, and then just move on. Just keep doing it. So in here, not only we are checking the changes of stabilizer, we are doing something with a logical gate to do the quantum operation. And every time, so every timing, every cycle is one step of this measurement, one step of measurement. And we kind of record all the configuration or signature of this stabilizer qubits read off. Okay, so just move on. So, and then we collect all the data later, and then see, okay, so this one has to be the error at this timing, and this error has been occurred in this timing, and so on, and recalibrate the result. So if this were the error, if there were no error at this timing, what would be the result? And we kind of, trace back and then kind of simulate the whole situation again, and then recalibrate the result with our finding of error correction later, not at the moment when we read the measurement qubit. Okay, so that's one picture. Any questions about this? Yes. I can share the code. This paper is okay, yeah. You can find the paper by this title. There is an archive. It's in the archive. Okay. Okay. So any other questions? All right, so let's look at others here. So what is a surface? What is the logical qubit? So the basic functionality of qubit is that it has X gate and Z gates, right? So not only stores some information, the only way we can identify what the information is we need to apply our gates and see what the result is. Okay, so let's say, so for example, we always talk about the cat 0, cat 1, or cat plus, cat minus. So in an idealistic way, but in real life, we don't know whether this one is cat 0, this one is cat 1. So it's all based on our measurement base or measurement qubit, measurement gate. So we take X gate and then it changes to another state. Okay, so then, and we know that it's eigenstate, then it's probably 0 or 1. And if we do the same thing with the Z gate, then you can see that it's +1 or -1, plus cat or minus cat. So here also, there are several data qubits, and we don't know how to describe it, but only way we can find whether this data qubit makes up one logical qubit is to apply our X logical gate and Z logical gate. And there are many ways to define X logical gate. The blue one is one way we can define it. So it's the chain of X running through the left boundary to the right boundary. So it consists of 5 data qubits. The X gates on 5 data qubits. And there are Z chain running from top to bottom, composed of 5 Z gates on 5 different data qubits. And it shares one common data qubit. And when you apply X logical gate, it means that literally you apply X gates on these data qubits. Okay, that's your logical X. So let's say you initialize your surface code by taking the first cycle of surface code cycle, and then you take the measurement and you get the signature of all the stabilizer readout, and then you take X stabilizer or X chain, and which means that you take X gates on these data qubit. Then it means that you apply X gate on the logical qubit, whatever it was when you first initialized. So let me emphasize again. So every qubit on the surface code in a real life, there is no difference between the stabilizer and data qubit. We just define this to be stabilizer, this to be data qubit, and every qubit comes with the gates, X gate, Z gate, and C0 gate in between next to each other. So, so data qubit also has all the basic operation we need. For example, ground state initialization and X gate, Z gate, and C0 gate to nearby qubits. And same for the measurement qubit. Okay? So if you don't have this functionality on the physical qubit, you cannot do anything on the stabilize, or you cannot do anything on the surface code. This just is just basic functionality. And why this X gates, X chain or Z chain serves as logical X and logical Z? Because it shares only one data qubit. So if you take this Z chain as a logical Z and X chain as logical X, if you change the order of multiplication, it gives you the negative value because of this Z gate and X gate applying on the same data qubit. And if you change the order of multiplication of XZ on the one single physical qubit, it gives you a negative sign. So overall, it gives a negative sign. So X gate and Z gate, you can identify what that is by two identity. One is that you have Z square and X square equals to 1, and Zx equals to minus Xz. If you have these two identity, or actually 3, then anything can be served as X or Z, really. So the reason why we took X gate to be the simple matrix such as 0, 1, 1, 0 is because we took our basis to be 0, 1, 1, 0. Okay? That's the only reason why we had this matrix representation. So it really doesn't matter what the matrix is, as long as we change the basis, then on the new basis, this matrix, which satisfies this identity, will just turn into this one, right? So we're doing the similar thing here. So we have x chain. If you take the square of x chain, it means that square of all the x gates on each data qubit, you get the identity. And same for Z. Any chain, it has anti-commutativity between X chain and Z chain, so it satisfies all this inequality here. And the interesting thing is you don't really have to go in the shortest path. You can have a detour. For example, you can have X1, X10, X11, X12, and then you don't take X2 in your chain, skip it, so you're kind of taking a detour, and then X3, X4, X5. So this chain also serves as logical X. Why? Well, it satisfies this identity, right? And in fact, this blue chain, and the detour chain is actually same X logical gate. They are the same logical X gate. How can you say it's the same? The reason why is, so let's say we have X chain, this one, the blue one, and let's suppose that there is no error whatsoever, So every time you take a measurement, what actually happens is, so because there's no error whatsoever, there are not going to be any changes in the signature of the readoff of the measurement gate. And what actually happens at every cycle is that you activate all the X measurements of this X stabilizer here. When you take an X measurement, then you kind of making an X gate or applying an X gate nearby this X stabilizer. So you had an X chain, so X gate has been applied to all these data qubit, and every each cycle you kind of activating this X stabilizer or X gate nearby on the data qubit nearby X stabilizer. So on this data qubit you had an X gate coming from the X chain and X gate coming from the measurement X stabilizer, so it cancels out, and then you get this another X gates on the other data qubit. So overall, what left is here it's canceled out to be identity gate, and then X gate, X gate, X gate, X gate, and then going to the original direction here. So you can always alter your X chain by assuming that your nearby X stabilizer is making another X gate around this original chain, to make a detour, and really doesn't matter because whatever we do, whenever we make X stabilizer measurement, we get the same result. So your data qubit or the logical qubit state is not changed. So it doesn't matter. It doesn't matter whether you take a detour or not, because you always can retrieve back to the original one chain of X gates, so that without changing any data qubit state. So yeah, that's one idea. And same for Z chain. So you see there's a Z stabilizer nearby. So if you want to take a detour from here to here, then you can just activate this Z stabilizer to make Z gates on nearby data qubit here, and then canceling the Z gate here, so that you get the detour line here. Any questions about this? All right, so let's move on to another picture. So, okay, so this is about error thresholds. And all right, so here's an interesting one. So here is more idealistic situation about how to use surface code in real quantum computer. So you have a large data qubit or large qubit, lattice figure data qubits. And can you just make one logical qubit in this large collection of qubits? The answer is no. So you can make several logical qubits. So you don't have, you don't always get one logical qubit state. If you always get the one logical qubit state, means that you cannot apply complicated quantum circuit, which involves several quantum states. So several qubit state. So in this case, it gives you one example of making a single logical qubit state without using two outermost boundary. So here is one boundary. So it's a smooth boundary because it consists of X stabilizer on the boundary here. And then there is another boundary, which is also smooth boundary, consists of X stabilizer nearby. And you can see that this boundary is supposed to have this Z stabilizer inside, but there's no Z stabilizer, which means that we don't physically remove the Z stabilizer. We just simply turned off our Z stabilizer. Turning off means that we just don't take a measurement. That's all. Okay? If you take a measurement, then the data qubit is stabilized by its eigenvalue of that stabilizer. If you don't take a measurement, it's as if it doesn't matter, right? It's not stabilized or collapsed into eigenstate. So there's there are two ways of thinking about there is no Z stabilizer. One is you just run the surface code as if there is nothing going on, but you just omit the last step of measurement on the Z stabilizer. That means that you just ignore as if it's not there. And the second way is you actually don't operate the surface code cycle on this Z stabilizer. So just kind of ignoring it. So physically there, but practically you assume that there's nothing at this position. You assume that there's no qubit on here. So then what happens is you have two X stabilizer boundary, which is called the smooth boundary. Just remember the name because usually we go for the names instead of the X stabilizer. So X stabilizer boundary is called the smooth boundary. Z stabilizer boundary is called the rough boundary. So here we have two smooth boundary, and there are blue line connecting these two smooth boundary. So on the smooth boundary, you can make a Z chain because this X stabilizer can detect the Z error. So you want to make a Z chain so that it not only preserves the original state, but also it acts as the Z logical Z gate. And you make X chain to serve as X logical gate here. So it's along the Z stabilizer here so that any error can be detected the Z stabilizer along this chain. Okay, so this is one way you can make another way of making a logical state, one logical state in the surface code. So you can imagine that there are big surface. This is only a partial picture of the big surface code, and you can make one logical state by making one small hole nearby the boundary and connecting these two chains. So these chains are not real. I mean, if you want to apply X logical gate on this qubit, this logical qubit, just take X chain here and Z chain here. That's your one logical qubit. So you can make another picture like this right next to this, and then make another second logical qubit, and then this second logical qubit has its own X gate, logical X gate, and logical Z gate. Okay. So here is the picture, what I just said. So here, the picture is kind of flipped here. So we have smooth boundary, and there is a Z cut. So this is called smooth boundary, and this is called the smooth boundary, but it's inside the surface code. It's called the Z cut because the Z stabilizer is removed. So cut means kind of cutting out. So Z stabilizer is cutting out. So it's called Z cut. And there's another Z cut. So just don't think about this one yet. So just think about two pairs of Z cut and the chain, Z cut and the chain. So we have two separate logical gate and logical qubit in the surface code by this configuration. And what am I talking about? It's just the cut itself is not a logical qubit. I said the logical qubit always comes with a logical gate. So whenever you want to apply X gate on the, so let's say this is your first logical qubit and this is the second logical qubit. If you want to apply logical X gate on the first logical qubit, then you want to apply X chain like this one, XL1 here. And if you want to do the Z gate applied on the first logical qubit, you want to apply the Z chain, which is around the Z cut here. And same for the second logical qubit. Okay? So again, just don't think about XL here. If you look at the, this Z chain and X chain, and this Z chain and X chain, they are commutative. They are commutative. So each pair is anti-commutative because it shares the one single data qubit here. So this Z chain and X chain, Z and X are Z and X in a logical qubit. Same for here. But let's say XL1 and ZL2 have no common data qubit, right? So they can be commutative. So you can apply XL1 and then ZL2, and same as ZL2 applied and XL1, because it's just independent qubit. It applies to independent qubit. So you can imagine that this is one separated logical qubit, and this is another separated logical qubit, as if you have two physical qubits in real life. And this picture actually tells you that you can manipulate your X logical gate and Z logical qubit on a two or more logical qubit in a different way. So for example, you can apply XL instead of XL1, and then consider this XL, ZL1 and XL2 and ZL2 also serves as two qubit state, work as a two qubit state. Just the same way we had this ZL1, XL1, and ZL2 and XL2. The reason being is, how do you make XL? So you want to make XL instead of X1, then you had let's say you had an XL1, meaning that you have X gate on these three data qubit. Apply the X stabilizer inside of this big half loop here. Then yeah, so apply X stabilizer on this half loop. Then this XL, all the X gate on this data qubit is canceled out because of this X stabilizer on these three X stabilizer. And inside of this half loop, all the data qubit has X gate applied twice by the two X stabilizer nearby. So they are all canceled out, so nothing going on inside. But on the boundary here, you can have X stabilizer right here. When you activate this, there's an X stabilizer applied here, and also here, because of these two. And then you also have these two. So you have, instead of X1, you can imagine that there is XL and XL2 serves exactly the same way as if the XL1 is applied on these three data qubit. So what actually happens is you can, there are two ways of thinking about logical qubit with a logical gate. One is just pair this up, ZL1, ZL1, XL1, ZL2, XL2. Or you can make a pair different way. For first logical qubit, your Z gate is ZL1, but X gate is XL times XL2. So the chain goes long way like this. And second logical qubit has the same Z and X logical gate. So that is this, and XL2 is this. So that also serves as two qubit state and two logical gates on these two qubit states. So basically, the picture is about this. So there are many ways. But so what is the common thing going on when I explain the detour here? So whenever you want to see whether your change of your chain, so you can. So first of all, you can change the shape of your chain of X error or X gate or Z gate by thinking about activating the X or Z stabilizer nearby. So that's one thing. And whenever you change your shape of chains of X or chains of Z by activating the X stabilizer and Z stabilizer, they are just the same as before. So it's no difference at all whatsoever when you changed your shape with the activation of X stabilizer or Z stabilizer. because your state, quantum state, is already stabilized as an eigenstate of X stabilizer and Z stabilizer. So activating a small portion, activating one X stabilizer in here is not changing your eigenstate. So activating here is not changing eigenstate. So you have to be careful that when you take activation, we're not considering the error occurred nearby data qubit here. So we just think about the ideal state. So just ideally, we can't do anything we can activate any stabilizer in the surface code to make a change of our setting of X gate and Z gate. So here's the picture here again. So let me go back here. That's a 2-qubit state. Any question about this? Yes.
What is the purpose for these detours?
What is this detour or the picture before? This one? Oh, what's the purpose? Well, we don't need detour right now. I mean, just giving you an idea how you can take a detour. You can make another configuration of X logical gate by doing this. So right now, maybe may mean something because, so let's say you found that somehow if you really made a quantum computer and found that there are different error rates on the data qubits or stabilizer qubit in this range, in this array, then you don't want to use this. You want to go a little bit detour. Let's say even if it's long, maybe it has a lower chance to get an error. So then you want to make this one as your X chain instead of this one, which has a higher rate of error. So maybe that could be one way you can have a detour. We need a detour, but right now it's just the ideal situation. Any other questions? Okay, so let me go to the next picture here. So we talked about two different ways of making a logical qubit. One is using the outermost boundaries to make a chain. The second one is you get one boundary and one cut. Okay, so here is a third way of making a logical qubit. You make a two-cut. And these two cut has to be the same type of cuts. So here we have two Z cut here, the smallest Z cut you can make by turning off this one Z stabilizer. And here you connect these two cuts by X chain along this Z stabilizer to correct error, if any. And you make one logical qubit by thinking about Z chain here on one Z cut and X chain here, okay? So you don't think about Z chain here. Z chain is not here. Z chain is here. I mean, it can be here and not here, but you cannot have Z chain on both of these Z cuts. So if you have both Z chain on both Z cut, then you have a two data qubit connect to the X chain. So you're not gonna get anti-commutativity of what we need here. So this is one logical qubit with an X gate and Z gate, and you can make another logical qubit in a different configuration. Instead of a Z cut, you can have X cut, which means that you turn off your X stabilizer to have a hole here, and then you have an X chain around the X cut, and then Z chain connecting these two X cut. So it's a bit, configuration. You cannot go by side. You're kind of a little bit off the grid here. So anyway, you can have two logical qubit defined, or maybe several. You can make as many as you want, right? By doing this, if you have a large enough surface code, you can make as many as you want, not just one, right? So I made a picture of this big surface code just to give an idea, but you can make lots of logical qubit in one surface code here. But the problem is, so what's the length of the boundary here? So length is at most 4, because there are 4 stabilizer and 4 data qubit. Length is 4. So you cannot So your error rate, or let's say your error detection is bounded in these 4 data qubits. So you can detect at most 2 errors in 2 different data qubits for this set chain. If you had 3 qubits errored, you can't distinguish whether it was 3 errors or 1 error. Or if there is 4 error, actually, if there were 4 error on this chain, you don't really know whether it has no error or it was error. So the drawback of this having small cut is that you have larger chance of failing the correcting the error, because there's a higher possibility that some abnormality of going on. So in real life, you don't want to go for the smallest smallest cut or smallest chain. You want to go for the longest possible, not too long, but I mean the long chain and big hole, because you want to increase the length of your cut and length of your chain so that your error correction is successful as much as possible. But this is an ideal, just an idea about what is going on, how to make a logical qubit. So it gives the example of the smallest cut and smallest chain. So you cannot make it smaller than this, right? So this chain to a 4 length 4 chain cut is the smallest, and also you cannot make it smaller than this. I mean, you can maybe move this cut into here, but just two chain. Well, it's not impossible, but it's kind of it's too short, right? The 2 chain is too short. Okay, so another picture. Let's see. All right. So here another thing is. So we're comfortable. I mean, I think we are comfortable of how to initialize our surface code without any hole. So let's say we have a whole surface code, and we're not going to make a logical qubit with a cut. Okay, we're not going to make a Z cut or X cut, and that means we just measure entire measurement qubits, and this signature is going to be our data qubit, initial data qubit, and then we do something here. But if the situation is that we want to make a cut and make several logical qubit, the question is how to initialize our logical qubit. What's the process? So this paper introduced 2 different ways of initialization. One is the easy one, and the other is a difficult one. I would say hard one. So the easy one, I mean, there are pros and cons for each case. So easy one is really easy. So let's say you want to make these 2 X, was it X cut? Yeah, X cut here, and then make 1 logical qubit. What do? First of all, we took a measurement, just initialize it as if nothing is here. And then next time we just ignore we don't take a measurement on these 2 cuts. So here and here, there is physically X measurement qubit, but we don't take a measurement. And we just work right away as if this is 1 logical qubit with a X chain and Z chain like this. And well, that's very easy. So what's the problem? The problem is we don't have any control of what the ground state of this logical qubit is. We don't know what the ground state is. The only way, I mean, we don't have control. We know what the ground state is, sorry. So let's say we had a measurement here, and let's say it was 0, read as 0. Then our ground state is plus 1 eigenstate of this X stabilizer and Z stabilizer. So that's ground state. But if we had read of this X stabilizer as 1, then our ground state is minus 1 eigenstate of this X stabilizer, X chain here. So it really depends on what the last readout of the X stabilizer that will be removed to make an X cut. So it's easy, but we have to work what we have given at the moment. Okay, you might say, okay, so what if we make a cut to the stabilizer which reads as 0. Well, I mean, that's one way, but let's say if you want to make a hole right exactly at this point, right here, and you already configured where your logical qubit with 2 x cuts or 2 z cuts are, and you want to initialize it, you want to make this logical gate at once, then you really don't have any control what the logical qubit on here and here is about. So that's one way. That's one the drawback of using this easy way of initialization. But there's modification there. It's not hopeless. So let's say you had the +1. You had a 1 readout of this X stabilizer. So you have to work on with the -1 eigenstate. Then you just apply your X chain artificially, because you already had this X. So wait. So you had a 0, 1. So you have -1 eigenstate of your. Let's see. This is X stabilizer. X stabilizer detect the Z error. Oh, sorry. So this. Yeah. So if you read this X stabilizer as 1, that means it's -1 eigenstate of Z chain here, because it means that there is some odd number of Z error going on here on this 4 data qubit. So in that case, if you want to change it, switch it back to the +1 eigenstate of Z, you want to apply your Z chain artificially to make it revert it back to +1 eigenstate of Z chain. So you want to do something more. If you really want to initialize every logical qubit to the ground state, logical state, then based on your last read-off, you do something on the logical qubit. So that's the easy way of initialization. So just 2-step initialization. And the paper also describes the hard way or difficult way of initialization. Here is the follow. So don't look at the right, it's only on the left. Right is the reversing process, so going backward. So when you have a logical qubit and you want to remove it, then how do you do it? So it's just opposite, exactly opposite way. So the left figure is how to make a logical qubit with a 2x cut here. So first you start with nothing, okay? So everything is just fully measured. And then what happens is you make a big strip of blank here. So here inside there is an X stabilizer and data qubit, X stabilizer, data qubit, X stabilizer, data qubit, and everything. So you just turn off your X stabilizer, 4 X stabilizer in between here. And then what you do is you want to take a measurement on these boundaries that stabilizer here. So there are 6 here, 6 boundaries that stabilizer here to detect any X, so that's stabilizer, right? X error on these data qubits. Okay, so you still want to keep track of the X of the error detection here. And since we turned off our X stabilizer, it really doesn't matter what the Z error occurred. So Z error is not our concern. We just want to detect X error. And then if you had an error, and you can modify it later. And then what happens is you keep turning off the X stabilizer, but the data qubit, you don't want to turn off the data qubit. Data qubit is important. So you initialize your data qubit on these 3 data qubit, which is inside of this strip, to ground state. You initialize them as a ground state, which is cat 0 state. And then you turn your X stabilizer back on in between these 2 cuts. So leave the X stabilizer on these cuts unmeasured, so it's still turned off, but you turn it back on the 2 X stabilizer in between. Okay? So you get the 2 X cut, and then these logical qubit serves as one logical qubit with an X chain and Z chain here. So so it's complicated. So why do we need this? So first of all, we want to keep track of all the X errors in the data qubit here. And why do we need the initialization of ground state in the data qubit? Because when we do so, then this logical qubit is automatically initialized as a +1 eigenstate of Z chain and X chain 2. So the ground state already gives you the +1 eigenstate of Z chain here, because ground state 0 cat is +1 eigenstate of Z here. Okay, and since we detected any X error here, everything is already stabilized by every X stabilizer. Okay, so we already detected and corrected, and kind of thinking that it is already corrected. So everything is fine with X stabilizer. So we don't have any issue with X stabilizer, but we still want the logical state to be +1 eigenstate, and that is guaranteed by the first initialization, the initialization step of these 3 data qubits here. If you want to, let's say, yeah, so that's important. So if you want the -1 eigenstate of the Z chain, then just apply the Z chain here afterwards. So this is something we cannot get, we cannot guarantee it by the easy way of initialization. So any questions about this? So this is a very complicated part. I'm summarizing what is written in the paper. So I hope you can just go back and home and read it if you want to. But I hope my explanation helps you understand this part of the paper. Okay, so maybe I'll move on to the important part here. Okay, so I think I should not skip this part. So the very interesting part is that once you have a X cut qubit or Z cut qubit, you can move your cut. So here you have 2 Z cut. So instead of X cut, it has a Z cut figure. So originally it had a 2 Z cut here, but you want to move your Z cut to here. So how do you do that? So you first take a one-step elongation of your Z cut by turning off your Z stabilizer right next to this cut, and then your cut becomes larger, and then you turn back on the original Z stabilizer that was turned off. So and then you take X chain a little bit longer to the original to connect to the Z cut, new Z cut here. So you can move your Z cut, still get the same logical qubit. And also, when you do that, you can take a easy way or hard way, just as we did before. So you can keep track of what's going on. You can always detect an error if there is any in this process. So important part and thing is, so this is kind of explaining the several steps of moving your cuts. So this figure appears many times. So what I think I need to explain this. So there are 2 Z cuts here. I know that it's Z cut because it's a Z chain around the hole, so it's a Z cut. So if there is a shaded area, that means there's no Z chain around the Z cut here. So it's not serves as a it's not the same role as this Z cut here. So Z cut here is the cut whose boundary serves as a Z chain, which is that logical gate, and this is not. Okay. All right. So what I want to explain is how to make C0 gate. Okay. So far we talked about how to get the X gate and Z gate. That's just a chain or cut. But how to get the C0 gate? That's a very interesting thing, because C0 gate is physically applied in the physical qubit in the surface code configuration, but we want to make a C0 gate for logical qubit. How do we do that? So this paper explains very important part of this quantum computer. And as I said, X and Z is not fixed gate. It's just representation of what is going on. And same for the C0 gate. So C0 gate is kind of change. It's a operation that changes the state of an entire 2-qubit state, right? So think about any gate, any quantum gate. It's an operation. It's a linear transformation. It changes the quantum state to another quantum state. So in other words, if you change the quantum state, it's the basis that changes. Your basis of observation is changed. So you want to understand how does the base changes when you apply the CNOT gate as an operator on 2-qubit logical gate, a 2-qubit logical state. So when you do this, so you have 2-qubit, right? And you had an operation, and there are 4 types of operation, consist of this X and Z here. And if you change the quantum state, 2-qubit state with a CNOT gate, these operations on 2-qubit state is changed into these operators, these operations. So it's a very, so I'll explain if you have, so think about this carefully, and if you have a question, I'll make a question and I'll explain it next time, more detail. So when you think about operation, and you think about operation as a change of the space in a basis of observing the state, observing the base vector space, then the only way you can detect it is by thinking about how the operator is changed to another one. So here, your CNOT gate is something that changes the basis, and you can see how it changes the basis is only detected by how the operators on that 2-qubit state is changed. So this identity is the exact identity that defines the CNOT gate. If anything, if you have X and Z step operator, if anything satisfies this, then you can call this as a CNOT gate. So what you want is, you want to find an equivalent operation that does this. Okay? So let's look at the first one. You have identity gate on the first, let's say this is first qubit on the left, the first qubit, and X gate on the second qubit. When you change the entire state with the CNOT gate, and you see the different bases, see from the different bases after changing the vector space, it's the same identity gate on the first qubit and X gate on the second qubit. Okay, remember this equation. And look at the picture here, and not here. Here, and not this one. IX, yeah, this one. So this is one. This one is the first qubit. This one is the second qubit. So here we have a Z cut and X cut. So you can change the situation, but just set as this. So these are 2-qubit, two logical qubit state. And what we're doing here is move this Z cut, one Z cut here, around another X cut of another logical qubit. So around this. So this is called a braid transformation. Braid means that you kind of making a knot, right? So like intertwining the strings. So anyway, so when you braid around this loop, this hole, you're just doing nothing because there's no chain at all. This is identity gate, so there's no gate at all. So when you do this, nothing's changed. So it doesn't feel anything. I mean, just something going on without doing anything. So it's originally Xi, the identity gate, and X gate here, right? So when you just braid once, you get Ix, the same Ix after doing this. So now let's look at the second equation here. Second equation says, if you change your perspective with respect to the CX gate, then Xi is changed to XX. Okay, that's the second identity of the CNOT gate. Remember this formula, and look at the picture above here. So we do the same braiding. So the trajectory of braiding is the same, and our first setting, the Z cut and X cut is the same, but only difference is that we have X gate on the first logical qubit and I on the second logical qubit. So we do the braiding. So here we don't have a Z chain here. So only we elongate the X chain here around this hole. Okay. So this is the picture. Just elongate. So move around the cut means that you just make a X chain longer and longer. So when you come back to the original place, what happens is you have all the X gates applied on the data qubit. How could you do that? So we want to see the equivalent to this situation. So there are X gates on these data qubits, X gates on all these data qubits. You could have done this by turning on X stabilizer inside but outside this hole, right? Here, right? So when you do that, so again, this whole surface code, we assume that there's no error whatsoever here. So when you take the X stabilizer turned on, your data qubit state or quantum state on the surface code is not changing at all. So when you turn on this X stabilizer, the X gates on these data qubits is turned off because of the X stabilizer. But inside, it's turned back on because of the X stabilizer. The same X stabilizer right here. It's turned on. Okay? So after all, your X chain got shorter to the original X chain. But instead of these big X chain, you get it smaller, right around the X cut, which was not there in the beginning. So when you do that, Xi becomes XX, okay? So your braiding made Xi into XX. And we can see the next one here. It's almost done. IZ becomes ZZ. So here on the left, it gives you this picture. So IZ. So here I is about Z chain, Z cut here. So we have I here, and Z chain is here. So we're not talking about X chain or Z chain. So Z chain right here. And when you do the same braiding, when it comes here, you kind of push it forward, kind of make it this short line into a little longer line. So it's kind of pushing it over here, over here, over here, over here, all the way up to here. Okay. So when you do the braiding, nothing happens. So it's an empty blank is pushing this chain over onto here. So your jet chain is getting longer around here. Right. So let's see how it can make it equivalent. So along the way, inside of this circle, inside of this, strip, there is a Z stabilizer. So I want to turn the Z stabilizer on these Z stabilizer only, not all, just this Z stabilizer. It still be the same quantum state because everything is just stabilized by Z stabilizer. So when I turned on this Z stabilizer, all these data qubits are going to be turned off. The Z gates on these data qubits will be canceled out because of the Z stabilizer action. And then what is left is I don't turn on this Z stabilizer. So these Z gates are still there, but this one is also turned on. So therefore, we have Z chain or Z loop here. And also, if because of this Z stabilizer turned back on, this Z gate is now turned back on, so the Z chain is restored, but instead this Z chain still remains, which was not there in the original. So what happens? IZ chain becomes ZZ. So what we are talking about is if you want to implement the CNOT gate on the surface code, do the braiding. Doing the braiding gives you CNOT gate. Okay? We're not physically changes the quantum state. We are making a new logical state, which is resulted by some operation which has the same effect of this CNOT gate on this ideal qubit. So this paper, I think it's intentionally missing the last identity here. Zi becomes Zi. So I think you can do it on your own. Why is it true? So Zi means that you have Z here and I here, right? So think about the braiding again. And if you have any question, we can talk about it next time.